In this second presentation on frequency response function estimation, we will discuss how we can process the data in order to remove or reduce the influence from unwanted signal components. So, how can we estimate frequency response functions from measured signals with measurements error, and how can we then design an optimum estimation technique? That is the question. So in order to refresh what we have said earlier, what we want is a reliable estimate with as small errors as possible of the frequency response function between an excitation and the response. And as we know from earlier, the defining relation of this frequency response function is the response spectrum over the excitation spectrum. And as we know from the previous presentations, both these signals, since they are measured normally with digital measurement systems, they are finite length vectors with values sampled at certain time instances, and the sampling rate, and at a specific sampling rate. So, what kind of errors then needs consideration when we design this estimation procedure? Well, first of all, random errors, that is contributions from occasional signal components that does not occur regularly in the signal. Then we have, of course, also non-excitation contributions to the response. That is, if something else, well, what we want to measure is actually the response acceleration caused by this force, exciting force, Fm. All other forces that happen to excite the system and contribute to the measured response is unwanted. So we somehow must be able to eliminate or reduce the influence of these unwanted excitations. And then finally we have also, of course, errors that we introduce by simply processing the signal. So how can we minimize that kind of errors? In this presentation, we are going to focus on random errors and non-excitation contributions to the response. So how can we process the signal to reduce the influence of these two types of errors? Well, let's first consider then that we have a signal, and we measure this signal for a certain time. And random signal contributions now means that we have some kind of occasional occurrence contributing to the signal. It might be, for instance, in this point here, we might have a closing door that adds the response in an unwanted way at this time instance. And in statistics, as you know, the normal procedure to reduce the influence of something unwanted, the influence of something unwanted is to use averaging. We take the average of the signal. But how then should the average be taken in order to get a good result? Well, here we have the measured signal again. So what is done is simply that we divide the signal in segments, 1 segment, 2, and so on. In this case, it's up to 8 signals. And the signal segment length now, Tm, is defined as the new measurement time. So when we take the FFT later on, then this Tm will be the new period of the signal. So the frequency resolution after averaging will be 1 over Tm. that is one consequence actually of averaging, that we cannot have full frequency resolution anymore. So we sort of buy this higher signal quality with losing frequency resolution. So next step then, when we have divided in segments, is of course that we have to avoid leakage errors, so we have to apply some weighting window. And if, as you know, if the signal has a random character, it's a wideband signal with random character, then we apply a Hanning window. So all time segments we multiply with a Hanning window in this case, so that we get the weighted time domain weighted signal. Then we take the FFT, the fast Fourier transform of all weighted time windows. And of course then we get this line spectrum, one for each weighted time window. And then we introduce the averaging. So we sum, we introduce an ensemble averaging of these frequency spectra by summing all frequency components, the first frequency component of all these n spectrum we have, and divide with n. And this we repeat for all for all frequency components. And then, of course, we have obtained an average frequency spectrum like this. And this is our frequency domain averaged spectrum of the signal. So, another problem is that we have contributions from unwanted sources that contributes to the response. So how do we estimate the frequency response function in order to avoid this contribution? Well, the solution is to use the cross spectrum between the response signal and the excitation signal, because this spectrum is free from uncorrelated contributions in the ideal case. With uncorrelated here, we mean, of course, that the contribution here is the contribution in the acceleration signal or response signal is uncorrelated to the force or excitation signal. So if we start now with the defining a relation for the frequency response function between the response and excitation, it's, as we said before, the ratio of the response over the excitation. So what we can do then in order to introduce the cross spectrum is to multiply both the denominator and the numerator with the excitation spectrum complex conjugated. So this star here denotes complex conjugation. And what we get now is, in the denominator we get the auto spectrum of the excitation, and in the numerator we get the cross spectrum between the response and excitation. And when it will turn out then that the cross spectrum, when you estimate the cross spectrum average from this ensemble averaging procedure that we showed earlier, then it turns out that as the number of time segments go to infinity, then the contribution from the uncorrelated parts, components between the response and excitation, will go to zero. Whereas in the auto spectrum, unfortunately, it will not go to 0. It will remain. So, usually, what is done, or often, if not to say always, what one should do is to try to select the best possible signal as the reference signal, as a source signal. So, in our case, in experimental structure dynamics, since you have full control over the force signal, if you use an impact hammer, then you can simply hit harder. If you use a shaker, then you can, then you have full control over the exciting force via the coil current that you input to the shaker. So, in our case, in experimental structure dynamics case, then it's almost always the force signal that is the best possible choice here. And you can treat this as if it were sort of clean from unwanted components. So this is the optimum frequency response function estimator in experimental structure dynamics case. So, in order to summarize now, we will discuss a step-by-step method for frequency response function estimation. So what you start with is, of course, to acquire the excitation and response signals with the data acquisition system. Then, as we've seen before, we divide the signals in segments that are synchronized and equal size. Synchronized is important because if they are not, you will introduce a phase error in the frequency response function. Then you take the FFT of the signal segments, and note now that the signal segments must be time windowed. You must apply this Hanning window, for instance, if they are random wide frequency band signals, in order to avoid leakage error. Then you calculate the reference signal autospectrum for all segments, JFF in our case. Then you calculate the the cross spectrum between the response and excitation for all segments, time segments. And then you calculate the average of the autospectrum for the force, excitation. And then you calculate the ensemble frequency average of the cross spectrum to obtain the best possible estimate of the cross spectrum. And then finally you calculate the frequency response function as the ratio of the cross spectrum over the autospectrum. So this is the optimum choice of frequency response function estimator in experimental structure dynamics.